Okay, we're recording. Great. So just to give you a quick recap of what we've done so far in this lecture. We've been talking about kinematics in one dimension. So that's motion of objects that are moving along straight line paths. And most of the previous lecture on Tuesday was devoted to defining things like position, displacement, and velocity. And we're about to move on to something called acceleration. But before we do that, I just want to point out a certain way we can visualize motion using graphs. So for the time being, let's think about an object that's moving with constant velocity. So in other words, as it's moving along, its velocity is not changing over time. It's just keeping the same constant velocity as it moves. So there are two types of graphs that we could draw to indicate how this object is moving. One would be a velocity versus time graph. So velocity goes on the vertical axis, time on the horizontal. And for this one, we would have just a flat line. This means we have the same exact value of velocity at all times. So this would be a flat line with zero slope. That's how we would indicate constant velocity, at least on this graph, right? But if we had a position versus time graph, remember, it's the slope of your position versus time graph that tells you your velocity. So if we're saying velocity is constant, that means the slope of this line is constant. So in other words, it's not curved. It's just a line with a constant slope. That's what it would look like. But what we're going to see is, if we allow the velocity to change over time, i.e. it's not constant, then on this graph, x versus t, we're going to see some kind of curvature, rather than just a straight line with a constant slope. Okay? So that's what we'll get into next. Is when velocity is not constant, we have something called acceleration going on. So we're going to define this, come up with some equations that describe acceleration, and then see what we can find out about acceleration when we're looking at graphs of motion. Okay? So let's start by defining something called average acceleration. Now, what we're going to do here when we define acceleration is very similar to what we did when we defined velocity. We're going to start with an average, and then we're going to use that definition to talk about an instantaneous value of that thing. So let's start with the average acceleration. So in general, when we say something is accelerating, we just mean its velocity is changing over time. If you're just moving in one dimension, just moving along a straight line, that means you're either speeding up or slowing down. It's really that simple. And the acceleration is a number that tells you how fast is velocity changing. So you have a very large acceleration if your velocity is changing very rapidly. If your velocity is not changing at all, you have zero acceleration. If your velocity is changing very slowly, you have a small acceleration. That's the idea. So we can define the average acceleration of some object that's moving in some kind of time interval as A average equals delta V over delta T. This is just the change in velocity on top, and then this is the time interval that elapses on the bottom. So remember, delta notation. The way this works is final minus initial when you see a delta symbol. So we have on top V final minus V initial for the change in velocity, and T final minus T initial for the time. Okay? So can you just remind me, velocity, what sort of units, let's say if we're working in the SI system, what kind of units would we have for velocity?
Meters per second.
Yeah, meters per second. Or more generally, the dimensions of this thing are length divided by time, correct? For velocity. But for acceleration, we have length divided by time, and then we're dividing by time again with this delta t on the bottom. So therefore, the dimensions of acceleration are length divided by time squared. And if we're using the SI system of units, we say that acceleration is measured in meters per second squared. So again, we're using meters for length, seconds for time, so our unit works out as meters per second squared. Does that make sense? So here's what we'll do next. Let's calculate an acceleration using this definition. The question here is, what is the average acceleration in meters per second squared of a car that goes from 0 to 60 miles per hour in 3 seconds? Okay, that's the question. So we go 0 to 60 in 3 seconds. What acceleration is involved in that process? Okay, so first of all, we're just calculating average acceleration using the definition delta v over delta t. Now in this problem, what is our delta t? It's 3 seconds, right? That's the time interval that's required to go from 0 to 60. Our delta v, let's expand this out a little more. Remember, that's v final minus v initial, correct? That's what we mean by delta. So what's my v final in this situation? 60, but it's in miles per hour. I'll write that as mph for here. And what's my v initial? 0. So that's a delta v of 60 miles per hour. Okay? What we want to do here is convert the units, because we have miles and hours, and here we have seconds. We want the whole thing to only involve meters and seconds. So in other words, I'm going to take this delta v, convert it to meters per second. So we have 60 miles divided by hours. I'll write it that way. So here's a unit conversion that you might not remember off the top of your head, but I'll just give it to you. In every 1 mile, there are 1,609 meters. So that's the unit conversion to go from miles to meters. Cancel that out. Okay, what about hours? I want hours to be converted to seconds. So what should I do to do that?
Do 3,600 seconds in a moment.
Yeah. So yeah, that's definitely true. I'm gonna take it in 2 steps. I'm gonna say in every 1 hour we have 60 minutes. So I'm gonna just go from hours to minutes like that. And then in every 1 minute we have 60 seconds. So I'm gonna go from minutes to seconds like that. So can someone crunch these numbers? It's 60 times 1,609 divided by 60 squared on the bottom, basically. What does that work out to?
Mm-hmm. 26.81.
Okay, 26.8, yeah, 82. And I'm going to put a little bar above the 8 because we're keeping 3 sig figs. We started with 3 sig figs before we did the unit conversion, so we still have 3. Now, unit-wise, we have meters per second. So in other words, 60 miles per hour is equivalent to 26.82 meters per second. So our average acceleration is this. We have 26.82 meters per second on top, that's our delta v. And then we have 3 seconds on the bottom, that's our delta t. And what does that work out to? Someone crunch those numbers for me?
8.94
And what are the units that we end up with?
meters per second squared.
Meters per second squared. You see that? We have 2 factors of seconds on the bottom of this fraction. So that's the number, but how do we interpret that? You can interpret that in the following way. You can say, every second that passes, the car is picking up 8.94 meters per second of velocity. That's really what that means, okay? So do you have any questions on that? All right then. So there's your definition of average acceleration, okay? Now, we're going to get to something called the instantaneous acceleration, because remember the average, well, it's an average over some time interval. Within that time interval, the actual acceleration can be changing. So if I just want to know what the acceleration is at one particular moment in time, instead of just averaging over a whole bunch of times, what I'm going to need is something called the instantaneous acceleration, okay? And the way we're going to get there is just through a little bit of calculus, okay? I'm just going to explain the concept here. Again, I'm not expecting anyone to make calculations based on this. I'm just going to explain the concept, and then we'll go on from there, okay? So, the concept that I want to get into here is the second derivative. Remember, last time we talked about the first derivative of a function. Now we're talking about the second derivative of a function, f of x. So let's say we have a function f of x plotted here. So the value of the function is on this axis, and then x, what you put into it, is on this axis. And then this black line is telling us, what our function is doing. So the way you can interpret the second derivative, the first derivative is the rate of change, right? The second derivative is the rate of change of the rate of change. That's how you want to think about it. So the way we write that is d2f dx squared. That's just how we notate this in math. But what does it look like on a graph when I have a function and there's a second derivative in that function? It looks like this. It looks like curvature. Okay? You can tell something about the second derivative of a function based on its curvature. And in particular, we have concave up curvature and concave down curvature that we can consider. So there's a pretty simple way to interpret this. If your function is concave down, like a frown, that's negative curvature, and therefore your second derivative has a negative value. That's what it means. Okay? And if your function in some other place is concave up when you graph it, then it has a positive second derivative, because it has positive curvature. Okay, so negative curvature, it's like concave down, positive curvature, it's like concave up. Make sense? What if it's no curvature at all? What if it's just a straight line? What does that mean about the second derivative?
Zero.
It's just zero. So if you have a straight line and it's not curved whatsoever, then your second derivative is equal to zero. Okay? And that is what's going to allow us to define this thing called the instantaneous acceleration. Again, this is when we say instantaneous, it's important to remember what this means. It means the acceleration at just one moment in time, as opposed to an average over a time interval. And so, the way we do this, just like we did with instantaneous velocity, is we take this delta t and we shrink it. We shrink it until it approaches zero size. So in calculus terms, what we're doing, so we're taking the limit as delta t approaches zero of delta v over delta t. Okay? And if you've taken calculus, you know that that's the derivative of velocity with respect to time. So acceleration is the derivative of velocity with respect to time. But velocity, if you remember from before, is the derivative of position. Okay? That means if we take two derivatives, or take the second derivative of position, that's also what the acceleration is equal to. So it's both of these things. You can think of it as the first derivative of velocity or the second derivative of position, okay? And with that in mind, remember, how do we interpret a derivative on a graph? It's the slope of that graph at a certain point, right? So if I have a positive derivative, I'm sloping up. A negative derivative, I'm sloping down. So if I have a v versus t graph, okay, it's the slope of that graph that's telling me what the acceleration is. In other words, if I'm plotting velocity this way, time this way, it's the slope of that graph that's telling me what the acceleration is. It could be positive or negative, depending on if the slope is positive or negative, okay? On the other hand, let's say I'm looking at a x versus t graph. I've got position here, time here. The curvature of that graph is telling me something about the acceleration. Remember, concave up, that's positive acceleration. Concave down, that's negative acceleration, based on what we said earlier. Okay? So we good on that? Really what I want you to take away from this, if the calculus is unfamiliar, are the last 2 points about how we interpret this stuff on a graph. Okay? So with that said, I want you to try out some examples. Calculating acceleration. So, what you have here is a graph of an object moving in one dimension, and its velocity as a function of time is shown here. So you have the velocity in meters per second and the time in seconds on each axis. So I'm going to ask you a series of questions, and in each one of them, the idea is I want you to calculate what the acceleration of this object is, okay? Based on the data given in the graph, okay? So let's try it at t equals 1 second, like right here. What would the acceleration of my object be at that moment in time? Remember, acceleration is going to be the slope of this graph. It's a velocity versus time graph. Acceleration would be the slope of this graph. So based on that, see if you can calculate the acceleration right there at that moment in time. Okay? So take a minute, try to work it out, and then we'll put it to a vote, see what we have. All right. We have our answers. Who thinks it's A? B? C? There you go. D? Okay, good. You get this? Just going to show you real quick my solution. Remember, A is equal to delta V over delta T. That's how we're defining acceleration. So I can read that off the graph as V final minus V initial divided by T final minus T initial. You can think of this as being the rise of my graph divided by the run. That's why it's equivalent to a slope, okay? So if we take a look at the time in question, T equals 1 second, there's basically a straight line on that graph, isn't there? So the far end point of that line has V final equals 4 meters per second. And we start at 0 for that line segment. And the amount of time that passes is 2 seconds, also minus 0. So that's just going to be 2 meters per second squared. That's how it works. All right? So let's do a couple other questions about the same graph. What about at t equals 2.5 seconds? What's the acceleration there? This one you don't even need to calculate anything. You should be able to just shout it out.
0.
It's 0, right? Because, I mean, just think about what it means to accelerate. It means your velocity is changing. So on this graph, what it's depicting is velocity is 4 meters per second all the way between 2 and 3 seconds. This entire segment of motion right here is constant velocity because the value is not changing over time. Another way to think about it is the slope is just flat at 0. So we don't have any acceleration going on. The answer is just 0. Okay. So the last question is this. What about at t equals 3.5 seconds, which is like right here? What's the acceleration? So take a minute. You can work it out on paper or try to do it in your head. Just take a minute to come up with an answer and see what you get. Okay, so what do we think? Let's just shout it out. What's the answer?
-2.
Yeah, it's answer choice C, right? -2. So first of all, we can rule out any positive answers because clearly the velocity is trending down. So this would be a negative acceleration. And if we want to just calculate real quick what that acceleration is, remember we're just doing V final minus V initial divided by T final minus T initial. So if we look at that last straight line segment, the final velocity there is 2 meters per second. You can read that straight off the graph. It starts at 4 meters per second, and then how much time in that last little line segment elapses? It's 4 seconds minus 3 seconds. So basically, we have minus 2 on top and 1 on the bottom. Units are meters per second squared, right? So those were just a few examples of how to take a velocity versus time graph like this and use it to say something about acceleration. Basically, it amounts to calculating a slope, okay? So this one is a bit more conceptual. So what's going on here? We have a graph at the very top. Let's just focus on this for now. It's showing you velocity versus time for some object that's moving in one dimension. So if this is the velocity versus time graph, there's also some kind of acceleration versus time graph for this object, right? Which one is the right one? Which one of these is correctly showing you what the acceleration of the object is, given that this is what the velocity is doing, okay? So again, how do we get acceleration from a velocity versus time graph? What feature do we look for? Slope. So what you should be plotting here is the slope of this graph. And there's only one answer choice that makes any sense. So try it out. See what you come up with. Talk about it to the person. Talk about it with the person next to you, and then we'll put it to a vote, okay? I think you got it? An idea? Okay. What's your thinking there?
If it's going sloping up, so it'll be that will be concave outside.
So I think you might be mixing up
Oh yeah.
position.
Okay.
All right. So you have to vote, okay? Who says it's A? Okay, who says it's B? Couple for B, C? D? E? So it looks like most of you got it. It is in fact A. Let me explain how I think about this, okay? So this is our velocity versus time graph right here. And we're trying to say something about acceleration based on the information here. So what we'll use is the fact that acceleration is the derivative of this graph, or in other words, the slope of this graph, okay? So we're going to break it into chunks, right? We'll look at this first couple seconds here, then between 2 and 4 seconds, then between 4 and 5, and so on. We'll just take it in pieces. That'll be the most easy way to go. So for this first bit of the motion, what can we say about the slope? We don't need to put a number to it, just is it negative, is it positive, or is it 0 right here? So we have positive slope on the velocity time graph at this moment, so we have positive acceleration, right? Is the acceleration changing at all over the first 2 seconds? No, because it's just a constant slope. If you have a straight line on a graph, the slope is just staying the same, okay? So we should have a positive acceleration at first, which is constant. So I'll draw that. See, I have a constant acceleration, which is positive. That's what I'm showing here. All right, so for the next moment in time, what can we say about the acceleration? It's 0, because we're maintaining a constant velocity for that part of the motion. In other words, there's no slope, and we have no acceleration. So that's pretty easy. A is equal to 0 between 2 and 4 seconds. And then what about between 5 and 6 seconds? We have another positive slope, And then that means acceleration is positive. It's also constant for the same reason we said before, because you just have a straight line on this graph rather than something that's curved. And how do we compare these accelerations, let's say here and here? Which one's bigger? The second one, right? This is a bigger acceleration. So I want to show that too on my graph. So we have a second where we have just constant acceleration, which is bigger from before. All right, so next we move on to between 5 and 6 seconds, where we have a negative slope. And it's kind of symmetric, so we should just be down here by the same amount as before. So there it is. And then we have over here, how much acceleration?
0.
0. And then we have another negative acceleration here. So there's our acceleration versus time graph. That's how we know. Okay? Any questions on that? Okay. So this is a pretty simple question, but it's going to get us to an important point. Suppose that we have an object and its acceleration, its value of a, is something negative. Okay, so a has a negative value. Does this mean the object is slowing down? Does this mean for sure the object is slowing down? So, what do you think? Let me just get your initial gut feeling on this, okay? Who thinks negative acceleration just means you're slowing down? Who thinks no, there's more going on? Okay, so you're right if you said no. There's more going on than just saying negative acceleration equals slowing down, okay? And actually, the way I want to convince you that that's true is by just drawing a graph of an object's motion and seeing what we can find out about that motion from the graph, okay? Okay, so here, I'm going to draw a position versus time graph. X versus t like that. And we want to say that the acceleration is negative. A is less than 0. So what does this graph look like, generally speaking, if I have acceleration and it's negative? So remember, acceleration has to do with the curvature of this graph, right? Because we're doing position versus time. Acceleration has to do with the curvature. What kind of curvature do we have? Concave down. Negative acceleration means you're concave down on an xt graph. That's what it means. Okay, so I'm just going to draw something that's concave down. That's negative acceleration. So it's kind of like an upside down parabola, right? And I'm going to just mark right here where the peak of that parabola is located, okay? So I just want us to look at, what's going on before we hit the peak of the parabola, what's going on after, okay? Okay, so here, before, let's say we're on this side, what can I say about the velocity of this object? Positive or negative? So, so we're just looking at this region before the peak of the parabola. It's positive velocity, right? So if I take any point, I draw the tangent line, it's going to have a positive slope, right? So right in this region, we have positive velocity, and we have negative acceleration, right? What about on this side of the peak? What do we have for velocity? Is it negative or positive?
Negative.
It's negative, because if I draw the tangent line here, it's sloping down. So we have a negative velocity and a negative acceleration, okay? So again, just on this side, we have a positive velocity with a negative acceleration. On this side, we have negative for both, okay? Now, on this side, what would we say is happening? Is this object speeding up or slowing down? No, it's actually slowing down, because remember, the sign of velocity, whether it's positive or negative, that has to do with which way you're moving. If you're going in the positive direction or the negative direction. But how steep the slope is, that has to do with your speed, how fast you're moving. So if we kind of follow this along, we're actually initially moving super fast because the slope is very, very steep. And it gets less steep. And actually here, it goes to 0, doesn't it? So we're slowing down. We're heading towards 0 at first, aren't we? So definitely I would say we're slowing down at first. But afterwards, what's going on? The speed is increasing because this line gets steeper and steeper. So what's happening here is velocity has a negative value. That just means you're moving in the negative x direction. But if it's a large negative number, that means you have a very large speed, okay? So here, we're speeding up, okay? Here, let's just, to totally drive it home, okay? What does this actually look like when something's moving in this way? Looks like this. Let's say that direction is the positive x direction, right? So I'm starting off with a very high speed coming in. So I'm already moving really fast this way. But I slow down and eventually come to a stop. Then I turn around because my velocity has reversed its direction. I start going the other way. I start going the other way with a faster and faster speed. That's what's going on here. So I come in with a very fast speed, slow down to a stop, turn around, speed up this way. That's what's shown on this graph, okay? So what do we have? We have negative acceleration and we're speeding up. So that's possible, right? That's what I'm trying to show you. So, how can we kind of organize our thoughts about all this stuff, okay? So an object does not necessarily have to be slowing down because it has a negative acceleration. Here's how we want to think about this. When velocity and acceleration have the same sign, that just means they're like both positive or they're both negative, they have the same sign, then you're speeding up. If they have opposite signs, that means your acceleration is going against your velocity. That's what it means to be slowing down. It's your acceleration is going against your velocity, okay? And sometimes we call this deceleration when you're slowing down. So here's a table that explains all the different cases, okay? So here we have A is positive, V is positive. What's going on in that case? Well, V is positive means we're moving in the positive direction. And because the signs are the same, that means we're speeding up. So acceleration and velocity are both positive, we're speeding up. What if acceleration is positive, velocity is negative? Well, because velocity is negative, that means we're moving in the negative direction. And also, because they have opposite signs, that means we're slowing down, okay? What if A is negative, V is positive? Well, positive velocity means we're moving in the positive direction, but the opposite signs mean we're slowing down. The last case is this, they're both negative. That means we're moving in the negative direction, but we're speeding up because the signs are the same, okay? That's how you want to think about this. So any questions on that idea? Anything at all? Okay? So we'll keep it moving. So at this point, I just want to drive home. You should have a sense of when an object is speeding up and when an object is slowing down. So I want you to take a look at this graph, which shows position versus time for an object moving in one dimension. So remember, x is the position, t is the time. And this is the curve that shows us how its position is changing. So we have 4 different points, A, B, and C. What I want you to do is figure out, at each point, are we speeding up, are we slowing down, or are we just moving at a constant speed that's not changing, okay? So the rules I just gave you in that table should be enough to figure this out, okay? So give it a try, okay? See what you come up with. So at each point, figure out what's happening. Are we speeding up, slowing down, or just moving at a fixed speed? this basically means at each point, you want to see if velocity is positive or negative, and acceleration is positive or negative. Did you already get this? Yeah. Did you get this one? Should check the first one, check point A. Because think about if we're even accelerating at that point. I'm trying to indicate the graph's kind of a straight line. Okay. So what do we think about, let's say point A, what's happening there? Yeah, we're just moving at a constant speed. Just so it's clear, I'm trying to indicate that there's just a straight line, at least for this segment of the motion, okay? So, just to sketch this out real quick. If I have my x versus t graph, and for at least some moment in time we have a straight line on that graph, there's no curvature. No curvature on a position time graph means A is equal to 0, okay? If we're not accelerating, we're not speeding up or slowing down, we're just, at least for the time being, moving at a fixed speed, okay? What about the second point, point B? What's going on here? Yeah, it looks like we're slowing down. I mean, one way you can think of this is we're moving in the negative direction at first. And then just after we pass by point B, we start moving in the positive direction. So we're turning around at some point, right? What do you have to do to turn around? You have to come to a stop. So we're approaching slower and slower speeds as we're coming to a stop. So we kind of intuitively see that that's the case. But let's think of it in terms of the curvature and the slope of the graph also, okay? So at point B, our x versus t graph, again, I'm just going to zoom in at the portion of the graph that's kind of around point B, which is like here. What can we say about the curvature of our graph? Is it positive or negative? Positive. Yeah, it's positive curvature. It's concave up. Another way of saying that is it's concave up, okay? So that implies A is positive, doesn't it? But what about the slope? What does the slope of our graph look like here? Negative. Yeah, it's negative. Draw the tangent line to the graph. It's sloping down. So we have negative slope. That implies V is negative, okay? Because we have acceleration and velocity going opposite ways, we must be slowing down. Okay? And then the last point, point C. What's happening here? So I'm hearing a little bit of both. We're speeding up here, okay? One way you can think about it is the graph is getting steeper over time. That indicates an increasing speed. We are moving in the negative direction, but the point is we're moving with a bigger and bigger speed as we go. And let's analyze this in the same way that we did the previous one. We have an x versus t graph. And around point C, it looks something like this. So what kind of curvature do we have?
Concave down. It's a negative curvature.
It's negative because it's concave down. Therefore, acceleration is negative, correct? Okay, what can we say about the slope?
Negative.
It's also negative. Draw the tangent line right there. It's clearly sloping down, right? So we have negative curvature and negative slope. That means we have negative acceleration and negative velocity. That means we're speeding up. Okay? So hopefully you're taking away what I wanted to emphasize about the sign of acceleration, okay? You have to look at it as it relates to your sign of velocity to really say if something's speeding up or slowing down. So, we good on that? Okay. So, I mentioned before that we can be dealing with motion at a constant velocity. Okay, that means you're not accelerating. We can also be dealing with motion at constant acceleration. This means you are accelerating, but the rate at which you're accelerating is not changing. It's just the same acceleration, that's not changing. Okay? So I want you to sort of get a picture of what this looks like when we graph motion with constant acceleration. So let's start with a velocity versus time graph. Remember, acceleration is the slope of my velocity versus time graph. So if I'm saying acceleration is constant and it's not changing, that means this is something that has a constant slope. That just means it's a straight line. There's no curvature going on with my velocity versus time graph. It's just simply a straight line. We all see how that would be true? Okay, what about my position versus time graph? So on this graph, acceleration is the curvature. It's telling us about the curvature of this graph. So what is something with constant curvature? It's a parabola. Okay, because a parabola is just either concave up or concave down with the same amount of curvature throughout. So that's the lesson. If we have constant acceleration, x versus t looks like a parabola, and v versus t looks like a straight line. Okay? So it's important to know that. We have any questions? Okay, so that's the idea we're going to start tackling now is if we have motion with constant acceleration, what kinds of equations can we come up with to describe that motion? And what sorts of problems can we solve once we have these equations? So I'm going to show you something called the kinematic equations. And one thing I just always want to emphasize about these equations as we derive them and as we start to use them is that they only apply to situations where you have a constant acceleration. If you're moving in a way where your acceleration is changing over time, these things just won't apply. You'll actually have to use calculus to deal with situations like that, which means we won't really cover them in this class, okay? But just be aware that this only applies to constant acceleration sort of situations, okay? So with that said, here is how we're going to set everything up with our kinematic equations. So remember, we're dealing with one-dimensional motion. So we typically use x for the position of an object, right? We just track where it's located along the x-axis, and that tells us its position. So there are some variables that I want to define for you. We have basically what are called the initial variables and the final variables. So at time t equals 0, that's our initial state. So we have an object, and it's located somewhere at that time. We call that the initial position. x0 is initial position. We use x0 because it's corresponding with time 0, okay? Also, at that starting time, this object might have some velocity, so we'll call that v0. That's our initial velocity. Okay, we have final variables as well. So if this is the starting motion that's happening, sometime later, the object is going to be in a new position, and it might have some completely different velocity. That's the idea. So we're not going to necessarily say what that time is. This can be any time that you plug into the equation. We'll say sometime t later, we're at our final position, which we just are going to call x. Okay, so if there's a 0, that means initial. If there's not a 0 subscript, that's just the final variable. Okay? So we're located at position x, and we're moving with some new velocity v. Okay, that's the setup. So the entire point of the kinematic equations is to relate what's going on here to what's going on here. If we know what the starting motion looks like, can we calculate what the object will be doing some time later? That's the whole point of our kinematic equations. Again, these only apply to constant acceleration. Okay? So what we're going to do next is derive all of these kinematic equations. We'll summarize the equations, and then we'll start doing some problems where we get to use the equations. Okay, so right now we're going to move on to deriving the equations. All right? And this is just going to be kind of on pen and paper. So here we go. We're going to derive our kinematic equations. Okay, for the first one, I'm going to start with the definition of acceleration. So the average acceleration in some time interval, remember, is delta v divided by delta t. Okay? But what we're dealing with is constant acceleration. So an acceleration that's not changing. So for this reason, I can set this equal to my instantaneous value. Does that make sense? If my acceleration doesn't change over time, then the average value is just whatever instantaneous value I have. Let me just show you on a graph what I'm thinking. So if this is acceleration, this is time, this is showing a constant value. Instantaneous means I'm just going to pick out some point. Say there's the acceleration. But since the acceleration is never changing, if I just average over the whole thing, I'm going to get the same value. So in other words, there's really no distinction between instantaneous and average, as long as acceleration stays constant, right? So with that in mind, I'm going to do something to the delta v over delta t expression that you see here. So remember, the notation that we're using is v. That's our final velocity. v0 is our initial velocity. So v minus v0 is delta v. Okay? And what about delta t? That's how much time passes, right? Our final time, we're calling that t. And the way these equations work is you start the clock at 0. So the starting time that you plug into the equations as we see them here is always going to be 0. Okay? So this just says a is equal to v minus v0 over t minus 0. So let's just rearrange that. We just have a t on the bottom here. Let's multiply that across on both sides to give us v minus v0 equals at. Just do a quick rearrangement of that equation. We get v equals v0 plus at. That's our first kinematic equation. What does it let you do? It lets you plug in a time, and then it pops out the velocity of your object at that moment in time. So if you know the starting velocity and you know the acceleration, you can calculate the velocity any time later using this equation. That's the idea, okay? And of course, we'll get practice using it, but that's what it's telling us for now. Okay, that one is pretty straightforward to derive. Basically, just if we know what acceleration is, we can get right to this. For the second equation, here's what we're going to do. So if acceleration is constant, the a versus t graph is just a flat line because acceleration is not changing. If I have constant acceleration, what does my v versus t graph look like? What does my velocity versus time graph look like? Remember, this is going to be a straight line. It's not going to be flat necessarily, but it's not going to be curved. Because remember, acceleration is the slope of this graph, and what we're saying is that slope is not changing. So it's just a straight line. Does that make sense? Okay. So here, check this out. This time right here is t equals 0, isn't it? What is the velocity at that time? We're calling that v0. So I'll put v0 right there. And then let's just indicate some random time later. This is just, can really be anything. Let's call this time t right here. The velocity at that time is what we call v, right? So this is saying we start at velocity v0, we end up at velocity v. Okay? What if I took the exact midpoint, like right here? So the exact midpoint between my starting and ending velocity. And what if I just went ahead and took an average of those two? Well, that would just be what we call our average velocity, right? So if I start with kind of a small velocity, end up with a larger one, averaging those two out, right where this midpoint is, would be our average velocity, okay? So that's what I want you to see here. How do I take the average of two different values?
You add in and then divide by 2?
Yeah, just add them together, divide by 2. That's how we take the average of two values. So I'll do just that. I'll add them, v plus v0, and divide by 2. Okay? All right, but do you guys remember from the last lecture, there's actually a separate equation or a separate definition of v average that we've seen before. Do you remember what it is?
Delta x over delta t, correct?
Yeah, so I'm thinking delta x divided by delta t goes right here. So we have like two different ways of thinking about the average velocity is what I'm trying to show you here, okay? But average velocity is the average velocity. It means I can set these two equal to each other, okay? And that's what we'll do next. Set the two expressions for average velocity equal to one another. And so what we end up with is v plus v0 divided by 2 equals delta x over delta t. All right? So let's rearrange what we have here. I'm going to keep the left-hand side the same, v plus v0 over 2. But on the right-hand side, I have a delta x. What does it, again, mean to take the delta of a quantity?
Initial, final minus initial.
This is final minus initial x. In our new notation here, for the final x, we just call that x. For the initial, we call that x0. So I'm going to write this as x minus x0, okay? And then for delta t, that's just t minus 0, because our initial time is 0, okay? So that's what we have. But check this out. V, my final velocity, I have an equation for that right up here. So where I see v in this work, I'm actually going to substitute in my very first kinematic equation that's in the box, okay? So I'm going to say sub in first dq. Okay, so on top, we have v, which is v naught plus at plus v naught right here. There's my substitution. Divided by 2 equals x minus x naught over t. All right, so all we have to do now is just kind of clean this whole thing up, okay? So what am I dealing with? On the left-hand side, I have v naught plus v naught. That's just 2 times v naught, right? 2 times v naught plus at divided by 2. On the right-hand side, I'll just keep it the same. X minus x naught divided by t. By the way, when I say v naught, I just mean v0. That's the same thing. All right, so 2v naught divided by 2, what does that equal? Just v naught by itself, right? Undoes the 2. But here, at divided by 2, I can write that as a half at. And then I'll keep the other side the same. Next thing I'll do is just put this t, which is on the bottom on the right side, and throw it over here. Just multiply through by that t. So what do I have? I have v naught times t, and then what does this term become? When I put the t on this side,
Half AC squared.
it's half at squared. That equals x minus x naught. So then we're,
Oh, we can.
Paper though.
oh, I'm sorry. Yeah. So here, to finish this off, x, just throw the x naught on this side, it becomes positive, right? X equals x naught plus v naught t plus a half at squared. That is our second kinematic equation right there. What does it tell us? Well, it tells us where an object would be located. It tells us the x value. X is position, right? So if I plug in my starting position x naught, my starting velocity v naught, and I have to know what the acceleration a is, and then I plug in a time, I want to say how much later, how much time ahead am I trying to predict, this will tell me x, which is the final position. It tells me where the object is located. Okay? We good on that?
I have a question.
Yeah.
On B initial times T, you can get rid of T, right? Because V is meters over seconds or length over time.
Yeah.
So you can cancel that out and you get a position.
Yeah, that's right.
So,
Unit-wise, that's true.
yeah, unit wise. But I actually don't picture where that position could be, or if I can have another initial position, or it's gonna be a position in the future. I don't know how that I don't know what that value is.
It's going to depend on the situation.
Okay.
So for now, these are just variables.
Okay.
In a given problem, we'll plug in specific values. What I'm trying to show you here is just what are the equations. We'll get to some examples to see how to use these. And hopefully with the examples, they'll become more clear. Right now, I just want to get what the equations are on the page, okay? So we have one more to derive. And you know, this equation, here's how we want to think about it. I've already derived two. With this third equation, we're not really bringing in any new information. We're just going to take the ones we already have and then do some algebra with them. In other words, we're going to substitute out time as a variable in the equations. That's the goal. So in other words, we want to write an equation where we sub out or get rid of time. So the way I'm going to do that is by starting with the first equation. V equals V0 plus AT. Okay? So can someone tell me, how can I take this equation and then solve for t? How can I get it to say t equals something?
Throw V0 to the other side.
Yeah, so throw V0 over here, so I have V minus V0, right? And then what? Divide by A. Y'all see that? So that's how I can sub out the time. So I'm going to now take this expression for t, which I got from the first equation, and then put it into the second equation. That's the idea. So I'm just going to copy down the second equation. X equals x0 plus v0t plus a half at squared. Okay, out of that we get, I'm going to do a couple things here. I'm going to put the x naught on the left side. So we have x minus x naught on the left side, okay? Then on the right side, I have v0 times t, but remember, I'm making a substitution for t, which is v minus v0 divided by a. And then I have a half times a, and then that's multiplying t squared, which again, t is going to be replaced with v minus v0 divided by a. But I actually want to square that whole thing, okay? So we're gonna expand all this out, it's gonna get a little messy, but a lot of things will cancel and then it's gonna reduce to something simple. That's what's gonna happen next. So on the left side, I have x minus x0. Let's think about what we have on the right side. In my very first term, I have 1 divided by a. You guys see that? In my second term, I have an a on top, and then I have an a squared on the bottom after we actually square this thing in parentheses. So actually, this also has a 1 divided by a in it. What I'm going to do is just pull that out. 1 divided by a is common to everything here, so I'm just pulling it out as a common factor, okay? So that's already been addressed. Now we'll just deal with everything else, okay? So what do we have? We have v0 times v right here. Copy that down. Then here, I have v0 times minus v0. That's minus v0 squared. Okay? Now, what do I have over here? Well, I can't forget that I have this factor of 1/2. I need to include that. And I've already accounted for the 1 over a. So really, I just have v minus v0, that entire thing squared. You guys remember how to sort of expand this out? We have an expression like this squared. So it's gonna be v squared, and then we're gonna have minus 2 v times v naught, and then we're gonna have plus v naught squared. That's how this expands out, okay? And that, again, is all multiplying 1 over a. Okay, we're almost there. We have x minus x0 equals 1 over a. I have v0 times v minus v0 squared, just leaving that alone. Okay, I'm going to take this 1/2 factor now and distribute it into these parentheses. So I have 1/2 times v squared. Okay, here I have 1/2 times minus 2, right? So that's just going to be minus 1. The 2 and the 1/2 cancel. And that's v times v0. And then finally, I have 1/2 times v0 squared. So can you guys see any cancellations here? So this term right here is just canceling with this one right here. You see that? One is just the negative of the other. What else can I combine? Maybe this term with this term? Because they're both v0 squared terms, right? If I have minus v0 squared plus 1/2 v0 squared, what is that? It's just minus 1/2 overall, right? So we have x minus x0 equals 1 over a. I have 1/2 v squared from this. And then when combining these two terms, I have minus 1/2 v0 squared. Okay, so I'll write this in the following way. X minus x0 equals, so not only do I have an a factor here that I can pull out, but now I can pull out this factor of 2, because it's common to both of these terms. So it's 1 over 2a, and then I have v squared minus v0 squared. I'm going to take this 2a, and I'm going to put it over on this side. So what I have is 2a x minus x0 equals v squared minus v0 squared. And just one little rearrangement gives us the final equation, which is to take this minus v0 squared and move it over here. Okay? And that says v squared equals v0 squared plus 2a x minus x0. That's our third kinematic equation. Okay? So I just want to recap what these equations have to do with. They have to do with how position is changing over time and how velocity is changing over time when you have an object that's moving at constant acceleration, okay? So what we're going to do the rest of today, as well as pretty much all of next week, is problems involving these equations and how we can actually apply them. Okay, so right now it just may seem like a bunch of, variables on a piece of paper. We're going to start to get an understanding of what they mean and how we can use them. Okay? Any questions on that? So there's the derivation. And here's the summary. Okay, just to summarize. We're going to be dealing with these three kinematic equations, and they only apply to cases of constant acceleration. Here's the first one, here's the second one we derived, and here's the third one. One thing to note about the last equation, you see how there's this x minus x naught thing? Read that as final position minus initial position, which is displacement, that's our delta x. So I could just as easily put a delta x in there. It's really a matter of choice, okay? So we good on this? All right, let's get to some examples. I'm gonna start with a pretty simple one, okay? In this example, you are initially driving down the highway at 44 meters per second, and you lightly press on the brake pedal to start decelerating at a constant rate of 1 meter per second squared. The question here is, how fast will your car be going after after basically 9 seconds have passed, okay? So you start at this speed, you brake for 9 seconds, how fast are you going after? You should be able to do this using this kinematic equation, right? Because V0, what does this mean? In words, what is this variable called?
Initial velocity.
This is called initial velocity. Are we given an initial velocity? Yes, we are. We're given an acceleration, right? We're also given a time. We should be able to plug those all in here and get the final velocity out. That's what we want to do. All right. What are we thinking? Okay, so I threw a little bit of a curveball in here, right? We should be going slower than before. So remember, there's sort of a sign convention we have to follow for the acceleration to get this to come out right. But other than that, it's straight plug and chug. So let's go through it. What did anyone else get? You should be getting something smaller than 44, right? 35, right? Okay, cool. So you take V naught in this problem to be 44 meters per second. It's always good to just write down everything you know. So A, I'm going to insert a negative sign because we're slowing down. So if I'm going to plug in a positive value for velocity here, I better have a negative value of acceleration to indicate we're slowing down, okay? At 1 meter per second squared as our rate. And then basically, we also know a time, which is 9 seconds. So I always suggest when you're doing a problem with kinematics, just write down everything you know. And then write down what you want to know, which is the final velocity. So V without the subscript is the final velocity. That's what we want to know. So then just look at your list of kinematic equations. There's usually going to be one that kind of has everything you need. And that's V equals V0 plus AT. So putting in the numbers, we have 44 meters per second plus minus 1 meter per second squared for A and 9 seconds for time. Let's just think about the units real quick. We have meters per second here, don't we? I think maybe this was your question before. if I have meters per second squared and then multiply by seconds, what is my unit here?
Meters per second.
It's just meters per second. So we're adding like quantities. It works. So it's just 44 minus 9, 35. Okay? So that's a fairly straightforward example. Now, I'll give you a slightly more challenging one. And because we only have 10 minutes, I don't think there's enough time for you guys to try it out and then for me to show you the solution. So we'll just jump right to the solution, okay? Here's the question. We have a plane which is capable of accelerating down a runway at a constant rate of 2 meters per second squared. In order to take off, the plane must reach a speed of 27.8 meters per second. Wait, I think, oh, I'm sorry, yeah. So this is the one I'm trying to do. So we need to reach 27.8 meters per second to take off. The runway is 155 meters long. So the question is, will the plane actually be able to take off under these conditions? Okay? So this has a yes or no answer. So let me suggest how we could maybe tackle this, okay? Let's imagine the plane that starts at one end of the runway at rest. It has no speed. And then it accelerates down the runway. Now it only has 155 meters of runway to go, right? So we could ask, how fast will it be moving when it reaches the end of the runway? We'll get a number to that, right? And once we have that number, we can compare it to this. So if it's less than this, then we can't take off, right? If it's more than this, then we can take off. That's it. So here, for this one, I'm going to actually draw a picture. So here's the x-axis, which represents the runway that our plane is going down. And I'm going to call this position right here x equals 0. That's the start of the runway. And this position right here is 155 meters. That's the end of the runway. Okay? Doesn't really matter where I choose to put 0, by the way, as long as it's 155 meters away from the start. Okay? So when we're over here at the start of the runway, what is our velocity? What is our V0? What's our initial velocity?
0.
0. We start at rest. Final velocity, once we reach the end of the runway, is what we're trying to figure out. Okay? So yeah, the plane is now at the end of the runway, and it's moving with some velocity, which we want to figure out. Okay, great. So I suggested using the equation v squared equals v naught squared plus 2a x minus x naught. Okay? So let's plug in some things we know. I'm solving for v. So if I'm solving for v, I take the square root of both sides to not have v squared, but just v. Okay? What is v naught? What do we plug in for this?
0.
0. So I have 0 squared plus 2. What was my acceleration in this case? 2 meters per second squared. All right, and then how do I deal with this part? I mean, like I said, you could just think of this as the displacement delta x. How far do we move while going down the runway?
155 meters.
Yeah, you can think of it this way. It's 155 meters when we reach the end of the runway. That's our x value. And it's 0 at the beginning. So basically, what I'm plugging into my calculator is the square root of 2 times 2 times 155, sorry. And what does that come out to?
24.899.
So 24.9 meters per second. We agree? using this kinematic equation, we say, if we accelerate at this rate for 155 meters, that we're gonna end up at the end at 24.9 meters per second. Is that enough to take off? It's not enough to take off, right? We need 27.8. So the plane won't take off. All right, and we can end it there.